Here are a few things that we gain without too much more effort from all of our hard work just now. So I'm not going to write the proof of this one because it's pretty short, you can see it in the notes, and the really hard part is the theorem that we just got done proving, which will get used in the proof of this. So if you have two natural numbers, n and m, then they are in bijection if and only if they are equal. In other words, they have the same cardinality if and only if they are equal. In other words, n has m elements if and only if n equals m. There exists a bijection from n to m if and only if n equals m. So this helps us answer the question posed earlier. Does 3 have 4 elements? The question, does 3 have 4 elements, is the question, does there exist a bijection from 3 to 4? Initially, that's a hard question to answer. It seems like it requires a lot, because you have to consider any possible function from 3 to 4. And there are many possibilities for functions from 3 to 4, and you have to show for all of them that they're all not bijections. But here, with this, we can say definitively that 3 does not have 4 elements. Because if 3 had 4 elements, if there were a bijection from 3 to 4, then we'd have 3 wiggles 4. And from this it would follow that 3 equals 4. But we know that 3 does not equal to 4, because 3 is less than 4. Alright, so finally 3 does not have 4 elements. Another nice result, this one, is often called the Pigeonhole Principle, and this one is an exercise. Actually, before I talk about this, I want to make an important point about Theorem 123. I've seen people get too excited about this theorem and forget about the hypothesis that n and m are natural numbers, and instead just think that if two sets have the same cardinality, then they're equal. That is a huge mistake. This only works for natural numbers. If two natural numbers have the same cardinality, then they're equal. But the idea of cardinality, the idea of there being a bijection from one set to another, is a lot more general than the idea of equality. That's why it's a different symbol. So don't just look at this part. This is a theorem about natural numbers. It's not telling you that wiggly equals is always the same as equals. All right, so this result here also follows from our hard work above, and this will be one of your homework problems. And this one is called the Pigeonhole Principle. Basically, it just says that if x has more elements than y, then you cannot inject x into y. That's all. For finite sets, so these are finite sets, they have natural numbers amounts of elements. Okay, so precisely, suppose x has n elements, which does not mean x equals n, but means x wiggle n, and n is a natural number. So there's a bijection between x and n. Y has m elements, so there's a bijection y with m, and m is less than n. Then it's impossible to have an injection from x to y. A good way to think about it is x has too many elements for it to be possible to inject x into y. So if you had a function from x to y, then it must not be injective, meaning there must be two elements of the domain, two elements of x, that the function maps to the same place, to the same element of y. So just to see how what kind of arguments this lets you make in practice, let's do a silly example of the Pigeonhole Principle. So let's say x is the set of students in the course. So each one of you is an element of S. And I think the course has about 35 students. I'm not sure exactly, but let's say it's 35 elements. And let's make y be, so instead of y, let me call it L for the letters of the alphabet. So let's suppose L is the set of letters of the English alphabet. So there's 26 of those. And we do indeed have 26 is less than 35. So I guess it's not supposing that, no, that's just the case. Of course, in our course we have not actually defined 26 and 35, but it doesn't really matter. You know what I mean by 26. I mean next, 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 and so on, of 0, and 35 is next, next, next. Okay. So if I say next the correct number of times, then that's what I mean by these symbols. And the idea is, since 26 is less than 35, it's impossible for any function from S to L to be injective. So, for example, let me pick an example of a function. Let's say f, given a student in the course, f is going to map that student to their first initial, so the first letter of their first name. Then, the fact that f cannot be injective is telling us there are at least two students that get mapped by f to the same letter, meaning there are at least two students who have the same first initial. So that is an example of the pigeonhole principle. Since there are more students in the course than there are letters in the alphabet, any function from students to letters cannot be injective. So in particular, the function that takes first initials of people cannot be injected. So the pigeonhole principle proves that there are at least two students in the course that have the same first initial, just by comparing natural numbers.